welcome to the mole and mass relations. We're going to hopefully help you understand them. So let's talk about the mole. The mole is measured in chemistry like dozen is in baking. It's a way that we can compose the same number of things. 1 mole of anything is equal to Avogadro's number, 6.02 times 10 to the 23rd atoms or molecules, just like a dozen equals 12 of anything. So a dozen elephants would weigh different than a dozen ants, right? Same thing with chemicals. A mole is of different chemicals has different weights or mass. So a mole of calcium weighs 40.078 grams. A mole of barium, 137.33 grams. A mole of uranium, 238. A mole of potassium chloride, we take potassium plus chlorine and we get 74.551. Moles are a unit of measuring chemistry. It's what we use to understand things. Now, a mole of anything is that 6.02 times 10 to the 23rd atoms, so it's going to weigh different amounts, just like that dozen is 12. Same thing happens here. So we can have a mole of sodium and a mole of sodium chloride, and they weigh differently compared to a mole of fluorine. To find out what a mole of anything weighs, for instance, we need to take the formula and break it down. So here we have BaF2, which is 1 barium and 2 fluorines. We add them together and we get a mass for barium fluoride. We can do that with barium hydroxide, which is what this is, and it has boron hydroxide. It has 1 boron, 3 oxygens, and 3 hydrogens. And we get a mass for it, and that's how many masses are in a mole. So we can do that for anything. We just need the subscripts of how many of everything we have. To find percent composition, I like to do it this way. I like to set up my mass like this, where I'm adding up, and then all I have to do is add just a little thing to the right to figure out what it is. So I take calcium's mass, divide it by the total mass, times it by 100, and I get the percent calcium. I can do that for carbon, I can do that for oxygen, and I can get my percents. They need to add up to 100. So if you take it to 2 after the decimal every time, then you should get the right answer. Avogadro's number is that 6.02 times 10 to the 23rd. That becomes a very important number that you need to remember. If it's just an element, we call them atoms. If it's a group of elements, we call it a molecule. The mole map we have up on the wall in our room is like, that has the 6.02 times 10 to the 23rd on it. It sort of looks like this. So here we have our mole and we have our mass. We can go back and forth between mass and moles by using the ratio of the molar mass to the mole. And the molar mass is just what we just were adding up, or if it's an element, it's just the mass. Once I get to the mole, I can also go to atoms or particles or molecules. And so I can take that and I can go on and I can use Avogadro's number, which is that 6.02 times 10 to the 23rd, to go backwards and forwards there. I can also go up or down to volume at STP. Now STP stands for standard temperature and pressure, and we'll get into that a little bit more later. But we can convert, if it's a standard temperature and pressure, from a mole to volume. So this mole map becomes very important in the things that we need to do. You need to be able to do this without looking at a mole map. So this is just a help to get you started, to help you understand where to go. But notice there's basically only 2 numbers that you really need to memorize on here, and that's the 22.4 liters in 1 mole, and that's at STP, and it's 6.02 times 10 to the 23rd in 1 mole to go from moles to atoms or particles. To use Avogadro's number, how do we find out, like, what is the mass of 1 atom of hydrogen? We're going to use Avogadro's number to go backwards. So we start at atoms, we use Avogadro's number on the bottom to get to moles, and then from moles we go to grams using the mass of hydrogen. We can find out that an atom of hydrogen is equal to 1.67 times 4 times 10 to the negative 24 grams, which is the mass of a proton. Okay, notice we're using our factor label. Again, we're keeping track of the units. So, your turn. See if you can figure out what the mass of an atom of nitrogen is. Stop or pause the video, See if you can figure it out using what we just did. Okay, I'm going to bring you back and I'm going to show you it. Hopefully you kept track of the units. And you can see that a mass of one atom of nitrogen is more because it has more protons in it. Here the mass of an element or compound and the number of atoms or molecules present can be determined. So if I was given 46.25 grams of lead, then I could figure out how many atoms are present because I can go back and forth. So going back and forth, we make sure keep track of the units, and we're going to cut that off. All right, so let's see if you can do this, going back and forth, given the number of atoms or molecules present in the mass of an element or compound, you can determine. You are going to take 9.345 times 10 to the 21st molecules of sodium nitrate and find out how many grams are present. Okay, we're back. How'd you do? Let's see. Were you able to get 1.319 grams of sodium nitrate? If you were, great, good job. Going forward, and that's the end. So hopefully you'll be able to go back and forth using that mole map and be able to use that. We're going to be doing problems in class, so we'll see you in class.